Okay, welcome to the HPCIC 2026 Spack tutorial. This is the same tutorial that we do at conferences like supercomputing, but we do it for free and online. So hope you all enjoy it. We really enjoy doing these because we get a lot of folks from the broader community to attend, and it helps us keep the videos up to date for a tutorial site, so that more people can learn about Spack. All right. So for presenters, I'm going to be giving the overview and the concepts talk today. We've also got Greg Becker from Lawrence Livermore National Laboratory, Alex Scott from Livermore, Caetano Milan from Livermore, and Kathleen Shea from Livermore. We're going to be alternating who does what section, but yeah, there's 5 of us for both today and tomorrow. For the tutorial materials, you should all be able to find the slides, the ones that I'm presenting here, and the scripts associated with them at spacktutorial.readthedocs.io. So if you want to go there, I recommend opening that up and having it sort of alongside your screen so that you can follow along with the interactive parts of the tutorial. We basically, we teach from scripts so that you can, if you get behind, you can catch up, or if you want to spend a little more time on a section, you can do that. So visit there and you can follow along with all the different the different sections that we're teaching. We do have, and we recommend that you use the tutorial channel on our Slack to ask questions. It's just easier to handle questions there in threaded form, and we have the other presenters online to answer them, than it is to handle questions in the WebEx chat. It's just it gets very overwhelming to handle questions from this many people at WebEx. So go and visit slack.spack.io and visit that tutorial channel. This is basically an auto join app that you can use to join Spack Slack. So it should be easy. If you do have problems, then feel free to post in WebEx chat and let us know if you actually can't get to it. Also, if you are at Livermore for this tutorial, you have a lot of people who are. SSH connections to the VMs that we're using do not work automatically. You have to, at least from your laptop, they'll work from an LC machine. But you may need to go and open an egress request before you can SSH out of the lab. So check the chat for that. I think Alec and Greg are posting about it. And we have a lot of people on Slack, over 4,000 now actually, who can help you. So it's actually valuable to join Slack because if you have questions about Spack after this tutorial, you can always ask questions there. It's very busy. We get a lot of questions every day and try to help everybody on there. You should claim a VM instance here. So you can go to spack.io/tutorial VMs. You can either do this now or you can wait until right before the basic section. But if you want to get a head start, go to this URL, spack.io/tutorial VMs, and you basically just put your name in a cell within this table, and the IP you're going to SSH to is this one right here, so 35.91.36.120 or whatever's in that IP address column for the cell that you pick, and then your login is whatever the column header is. So for here, you would SSH to Spack2 at that IP address. We use VMs for these tutorials because normally using Spack requires a lot of building, and for the tutorial examples, we have binary caches in the VMs, and so it'll just be faster to go through the examples there for the class. So check that out, and we'll show this again before we start the hands-on section. Here's the agenda for day 1 and day 2. So we're on day 1. I'm doing the intro. We're going to spend about an hour and a half on intro, then some examples of sort of the basics of how to use Spack, and then I'm going to come back on and go over the core concepts once you've sort of seen intuitively how the tool works. We have sort of a talking section about sort of teaching you about what you just saw. There is a break at 10:30 a.m. for 5 minutes, and then we're starting environments at 10:35, and we're going to get configuration after that. And we'll be done at 12 p.m. So the first day I ought to give you the basics of how to use Spack as a user, just for installing stuff for yourself. And then on day 2, we're going to cover some more advanced topics. So day 2 starts with software stacks. where we show you how to build an environment that can do a full facility deployment with the combinatorial software stack and how to deploy modules with that. And after that, we're going to do packaging, so how to write your own Spack packages. There's another break. It's pretty short. And then we'll do developer workflows and how to set up mirrors and binary caches for your packages. So developer workflows is nice. You can actually use Spack to to work on applications under development. You can develop different components at the same time. You can use it to upgrade packages that you depend on, and so on. And then mirrors and binary caches is basically how to speed up your workflow by hosting the sources and binaries for what you're working on in S3 or on a website or in a file system. Right. So what's the point of all this? Modern scientific software is built from lots and lots of small complex pieces. Where this is a quote from Paul Dubois and Tom Epperly back in like 2003, just where they noticed that they've gotten large integrated codes working, but they said that just when they're starting to solve the problem of how to create software using reusable parts, it founders on the nuts and bolts problem outside the software itself. And so they wrote this paper called Why Johnny Can't Build. It's basically like a long complaining paper about all the hard parts of putting libraries together. What's hard about modular software? And today, thanks in large part to how much open source is out there, most software is component based. People reuse libraries from open source all the time. They try to put them together. It's useful to reuse things because we can't rebuild everything from scratch. Can't rewrite the world. Although maybe that's changing with LLMs. Although I don't know if you trust that yet. But you're now in charge of ensuring that all of the reusable parts work together. And so you can have build time incompatibilities where things fail fast, and that's usually good because all the nice static checkers like your compiler tell you that things are not going to work. Or you can have subtle errors later, and this is very easy to do in the build world. If you build one component slightly differently from the others, your flags are incompatible. If you use a version of a dependency that maybe the dependent wasn't meant to depend on, then things can explode at runtime in nasty ways. And so it can be very, very hard to manage lots of software components. And just to demonstrate, here's a few examples. This is MVEM. It's a fairly domain-specific library. It is for higher order finite elements. It does one thing lots of different ways. It manages elements for meshing in simulations. And this is like a relatively small configuration of MVEM, where you've got MFEM, you've got sundials and PETSI. These are solvers, Hyper, SuperLU, lots of different solvers in here, lots of different linear algebra libraries, all to manage the finite elements, some build tools, and so on. But there's 31 packages and 69 different dependency relationships in there. ML libraries are even more complex. So TensorFlow, PyTorch, and LBAN is shown here, where these are all neural net libraries. They're bigger. They have lots of different Python dependencies and also lots of different native dependencies. So this is 71 packages and 188 dependencies. And then in the interpreted language ecosystem, there are just very, very large dependency networks where, like, this is RCondup. It's a genome data analysis tool. You can see that it's got 179 packages in the dependency graph and 527 different relationships between them. This is the package itself. You can kind of see two pieces of this graph. The ones at the top, these are all the R dependencies. So all the stuff that's written in R. This is R itself, which is a native program. And then these are all of the dependencies for R and maybe some of the native dependencies for the R libraries. So there's complexity sort of on both sides of the interpreted compiled boundary there. Big codes are not immune from this problem. And proprietary codes aren't either. So this is Aries. It's an ICF code at Lawrence Livermore. And you can see from this graph that Aries is this little dot up here. It depends on almost 100 libraries. And while some of them are Livermore internal, so that's these pink ones, many of them are open source and developed at Lawrence Livermore. So they kind of live outside the lab on GitHub and are developed there by lab staff. And then all of this blue stuff is libraries that we don't control. These are libraries that we use from the open source ecosystem that we rely on, that we wouldn't want to rewrite because it's a ton of work. And about 80% of this code is open source. And so integrating open source packages is something that both proprietary and open codes have to do. It's not unique to just open stuff. So the point of all this is we need to be able to put these things together. Many package managers make assumptions to simplify this problem. And so if you look at, say, APT or RPM or the package managers that deal with your Linux distribution, there's typically a one-to-one relationship between the source code and the binary. So you have some source code and you have one way to build it that goes into the distribution. And maybe it uses like GCC as a system compiler, a particular version of GCC. It uses particular libraries. And it's meant to be upgraded in place over time in sort of a compatible way. And then if a new version of the OS comes out, then it's a new starting point and it's meant to be upgraded over time again. The binaries are designed to be portable. They're designed to run on lots of different platforms. And so they tend to be built with microarchitectures that do not take advantage of all the instructions on modern processors. And the tool chain, it tends to be the same across a distro ecosystem. So like most distros are using GCC as the compiler for all the packages in them. And this is really not how HPC looks. In HPC, we often have to build on different bleeding edge platforms, lots of different variants of the same package. You may enable or disable different build options depending on what you're doing. You may optimize for the processor or the GPU, so you have to care about the microarchitecture or the compute capability, and not doing that can make a 10 to 100x perf difference. The code's typically distributed as source, and so you want to be able to build this from source on the host machine. And despite all that, we also rely heavily on system packages. So on most of the big machines, we really care about using the system MPI. Because it's tuned for the network on the system. And the codes tend to be multi-language. So there's C, there's C++, there's Fortran, there's Python, there's R, there's Lua, there's lots of things that have to be linked together. So there's just a lot of complexity that sort of comes together in the HPC and also in the AI world. I think the AI packages are actually pretty similar in terms of how they're built, in that there's an interpreted language and there's a lot of native components that really rely heavily on hardware. And so that's what we're dealing with. What about containers? They can simplify things quite a bit. They're a great way to reproduce and distribute an already built software stack. So if you get something working and you did it in a container, then you can give someone the binary and they can go and reproduce it on a similar system. But someone has to build a container. And often, if you're developing an application over time or if you're updating different versions, you need a fairly modular way to build a container so you can build different versions of it for different machines, especially in HPC. If you just build sort of a lowest common denominator container, you're kind of doing the same thing that the distros are doing and building something portable that maybe doesn't take advantage of the hardware. You can use the OS package manager inside a container, but again, the packages are not necessarily optimized for the machine you're on, and you're probably going to need to rebuild your container to support different hosts, different architectures, different system packages, or different MPI implementations. Or maybe different, lower level networking libraries on your system. So we're really looking for more flexible ways to build containers. So that's the point of Spack. It was built to enable software distribution for HPC. When we built it, we were sort of fighting with builds on BlueJean and getting sick of rebuilding the same 12 libraries over and over again. It's designed so that you can just clone it and start using it immediately right out of the repository. And it's also designed so that you have some control over what you're installing. So you can say Spack install HDF5 at some version. So you can say, I want a particular version. You can specify what compiler you want to use. You can specify options. You can inject build flags, specify microarchitecture targets, and you can be particular about how things, the versions of your dependencies and the configurations of your dependencies. So here you're saying I want HDF5 with MPI and I want to use mbitch at a particular version. So it's really designed to both be sort of simple in that you can ask for the sort of basic configuration of something, but also complex enough and flexible enough that we can use it for cases where we really want something in particular installed for our HPC system. Spack's designed for lots of different users. We try to target basically all of the different parts of the user base. Anybody who really wants to use or distribute software for HPC. So that includes end users, like people who just want to install and run an app on a machine. It includes application teams who are effectively managing their own software distribution for their dependency libraries. It includes package developers, so people who build a piece of software and want to make it easier for other people to install it. And then finally, the original audience for Spack was user support teams at HPC centers, and they continue to use it quite a bit. So people who deploy really large combinatorial stacks of software for all their users to use at centers with thousands of different users. Spack's in HPSF. It's the High Performance Software Foundation, which is working with us on this tutorial series along with Livermore. And what that means is it has a neutral legal entity. So it's a 501c6 nonprofit. It's not owned, by Lawrence Livermore. It has its own technical steering committee that includes people from across the ecosystem. And you can see how the governance for the Spack project works here. So it's at github.com/spack/governance. The trademark is owned by the Linux Foundation. And what that means is that there's a pretty liberal trademark policy that allows people to use it as long as they are referring to the open source project and not saying like, this is my, derived enterprise version of Spack or something like that. And really, the goal of this is to make sure that the community continues to grow, that it's open, that there's not a worry that one organization could decide to make a big change and take Spack in a new direction that isn't really compatible with its user base. We're trying to make it out there and available and always usable and free for users. We don't do this alone. We've got the core team, but we sustain the HPC software ecosystem in Spack with the help of many, many contributors. So you can see here, when I started working on this in 2013, it was just me. There were people from Livermore who helped out until we sort of presented it at Supercomputing in 2015. And since then, we've gone from maybe 170 packages to almost 9,000 in the built-in package repository here, and then people maintain their own private package repos outside of that. And you can see that Livermore, while I guess we're still the biggest contributor to packages just by lines of code, that may be from comments and SHA-256s and things like that, just maintenance stuff. Most of the package lines, the lines in the actual package recipes, are contributed by other organizations. So you can see a list here. But that continues to grow over time. People continue to contribute more and more packages to Spack, and that makes it more and more useful. It's used all over the world. So you can see here hits on the documentation site. This is my best way to characterize who's using Spack because we don't really do analytics on the tool. We can see where people are coming from when they hit the documentation site, and so this is what you're seeing here. Basically, anywhere there's HPC, there's the Spack being used in some capacity or another. The GitHub site remains very busy. So this is showing the, 1.1 release on GitHub. So that's from October 16th to November 16th, 2025. This is 1 month. Every month we have, over 115, probably like 115 to 140 users working on the project at any one time. So you can see here, like we merge, anywhere from like 350 to like 500 or 600 pull requests a month. And we try to keep that moving over time. So it's a fast moving project. And there's always a lot of activity trying to keep the packages up to date. This is just showing how the project evolved over time. So I kind of already went through this on the previous slide, so I'll skip through it. But this is what it looked like in 2016, and that's this little sliver of the plot, and it's grown quite a bit. Spack's also been adopted by industry, so it's actually used by Amazon, Google, and Azure for their cloud HPC offerings for deployment in one way or another. Amazon helps us out with cloud credits for CI, and AMD, HPE, Intel, NVIDIA all contribute to the package repo to keep their packages up to date. And ARM, it's been very useful to have the kind of industry engagement we've been able to get by having sort of a center of mass around Spack as the way to deploy packages for HPC. Latest version of Spack is 1.2. I'm not going to spend a lot of time on the feature list here, but we do releases about once every 6 months. We may do those more rapidly now that we've sort of separated the packages out from the core repository. Since version 1.0, our goal has been that you should be able to, continue using the latest version of Spack with the packages that you have. And so we're sort of guaranteeing that the package release that we did around version 1.0 will continue to work for all the 1.x versions of Spack. So our hope is that while in the past, I think people, would sort of step their upgrades, I think you can reasonably stay on the latest version of Spack now and continue to use, the package repo version of your choice. And we're hoping to keep that going. We keep adding performance improvements. So 1.2 actually had a lot of performance improvements over 1.1 and especially over 1.0. We're starting to add security stuff. So experimental sandboxing and SBOMs were in 1.2. And then finally, Spack is not the only thing out there. There are lots of ways to manage packages for scientific software and for software in general. Spack is sort of inspired by Nix and Homebrew to some extent. So Nix and Geeks are so-called functional package managers. You'll see the hashing that we do for directory installations, and we're really that was inspired by these systems. There are build from source, although maybe not so much anymore, Homebrew, Linux Brew, MacPorts, and Gentoo. These package managers kind of inspired the internal source build model, and Homebrew sort of inspired this package format. But these are not geared towards HPC. And then pip and UV are sort of the package managers for Python. UV is adding a lot of cool features for managing just Python packages, although it does not cover the whole HPC ecosystem. And then in sort of scientific software in general, there's EasyBuild, which is probably our sort of closest, I guess, competitor, which is it's mostly an installation tool focused on system administration and deploying module stacks. It's a different model. Check it out and compare. And then Conda, Mamba, and Pixie should be pretty familiar to folks. Conda is sort of a binary packaging ecosystem, not build from source, where you can install lots of different scientific software. It's been big in scientific Python for a long time. And Mamba and Pixie are kind of faster and sort of more modern workflow evolutions of that that use the same package ecosystem. So check those out.
So here we're going to actually start using Spack in action. So the few fundamental ideas that underpin everything that we're going to do, just to reiterate as we start, is first that Spack can install software either from source or a pre-built binary. So we're going to show an example of both of those, but we're mostly going to be working with a pre-built binary for the tutorial to really speed things up. Spack isolates each package's installation, so this allows many versions, compilers, build options to all coexist on the same machine. You can have multiple installations of all of the same packages. Each installation is identified by a hash of its full provenance, so everything that makes it unique. And Spack reuses an existing build wherever it can instead of rebuilding from scratch. So we're really trying to save users as much time as possible here. So let's get started with actually just setting it up. So we're going to clone it off of GitHub. So we'll say git clone. We're going to add a dep equals 2 just to speed that up a little bit. And we're going to be going off of the most recent branch that we released at this point just a few weeks ago. So branch equals releases version 1.2 from our GitHub. So github.com/Spack, spack.git. And we're going to be just putting our Spack into our home directory in a Spack folder. So, or Spack repo. Oh, what did I do wrong? Oh, I forgot the slashes.
Kathleen, can you make your terminal like one notch bigger? And then a request. Maybe Diaz probably good.
Better. Okay, so then let's go into Spack for these examples. And then to set it up, we have to source the Spack setup script. So we're just going to do .share Spack setup env.sh. And now we're good to go. We can start using Spack as a tool. So before we install anything, let's see what Spack has to offer. So if we type the Spack list command, it gives all of the packages that are already in Spack's repo, so the packages that you wouldn't have to put in yourself. Also, this first time you run Spack list, it's going to be slower than all the other times, we promise. But as you can see, there's already over 8,900 software packages that you can use using Spack. But if you also wanted to narrow the list, you could pass in a substring. So if, for example, you're wondering which Python packages are in here, you can say Spack list followed by the string. So let's do all of the ones that start with pi. And first you can notice that it really did go faster and that we also have about 3,000 Python packages already in Spack as well. So once we've found a package that we want to install, it's just the Spack install command followed by that package's name. So we can say Spack install gmake just for this first example. And you can see that the compilers have already been configured, yep, there we go, it's installing. The E marker denotes if a package was found on the system rather than built by Spack specifically. But we can see that for this build, we have gmake, GCC, GCC runtime, glibc, and the compiler wrapper. So gmake is the package we requested. GCC is the compiler used to build gmake. Those are used as their own packages as well. GCC runtime and glibc are just records of the compiler runtime needed by Spack. And the compiler wrapper is a wrapper Spack uses to inject the right include library RPath flags when it invokes the compiler. We probably won't get too much into that right now, but we will later on. And if you have questions more about how Spack works, of course, we're always available to answer this. So in Spack, a compiler is an ordinary dependency rather than a special case. If some of you were using Spack pre 1.0, that wasn't the case. So now you have to explicitly request the dependencies or request the compilers and use them like any other dependency and package. So if you wanted to see what compilers we already have, you can just say Spack compilers or Spack compiler list, I think. But as you can see again, these E's are that externally on the system, we found these 3 compilers, 2 versions of GCC and LLVM. And then later on, we'll talk more about it in configuration. And also at the end of this section, we'll practice adding a tutorial or adding a compiler. So like we said, Spack can install software either from source, like we just did with gmake, or from a binary cache. But to speed up the rest of the tutorial, because we'll be showing a lot of power behind Spack and a lot of more complex builds, we're going to use the binary cache that we've already set up. So let's run Spack mirror add tutorial and look for it in /mir. And again, this is an important step for you guys to do to be able to follow along so it doesn't take hours. Then we need to trust the keys. Generally, obviously, this is not the best practice to do if you're going to be taking in a binary cache, but for this tutorial, it's okay. So we're going to say Spack build cache keys install trust -- yes to all. And now we should be good to go. So now whenever we run Spack install, if there's a package from the cache, when you ask to install that package, it'll install it from the cache instead of from source. So a main feature that we also have in Spack is the spec syntax is what we're going to constantly be referring it to. I think spec originally comes from a specification, so that just helps me that it's the exact specification of what you're trying to install and build. So far we've only been installing with the default configuration, but what makes Spack special is that you can specify it to be exactly what you want. So it specifies any constraints we want to place on its build, whether that be the version, the build option, the compiler it uses, and even the configuration of its dependencies. And they each have their own sigil for how to tell Spack that you want to specify those things or constrain those things. So let's get started with if you wanted to install a specific version of something, of a package. So if you were wanting to install zlibng and you're wondering what versions were already in Spack, you can use the command spack versions followed by the package. So spack version zlibng will show us all the versions available in Spack already. So say we want to build with an older one, we want to do 2.0.7. We're going to say spack install zlibng, and then we're going to use the @ sign to specify version. So @ version 2.0.7. And as a note, the @ sigil also accepts ranges. So if you know that there's a bug or something that's incompatible for you before in 2.0 and before, but you don't really care what it is after that, then you could just say @ version 2.1 and anything later with a colon following it. Or say the opposite, that something was introduced in 2.1 that you didn't want, but you're fine with any package before that, you can use the colon prior to the number after the @ sigil. So colon 2.1 would be up to version 2.1, or a range in between those two. So 2.0 through 2.2 is anywhere in between those versions. And then Spack's able to pick anything that satisfies that constraint without you having to figure out exactly which one you want. You can just generally say, I want it in this range. Besides versions, we can also have build options called variants. So if you wanted to see the variants a package defines along with what the defaults would be, you can use spack info. So let's say spack info, and we're just going to hide the dependencies for now to make it easier to show the variants. So we're going to add the no dependencies flag and also versions, the no versions flag of zlibng. So then here you can see there's like compat, generator, IPO, that's automatically set to false, the explanation of what those might be. So for example, this is like CMake interprocedural optimization. If you want that, then you could enable it, or if one's true and you don't want that anymore, you can disable it. And all that information is just available to you right here. So the Boolean variants, the ones that are true and false, like the ones we were just highlighting, are enabled with the plus sign sigil, and they're disabled with the tilde sigil. So for example, zlibng has an IPO variant that we were pointing to that enables interprocedural optimization. So if we wanted to turn that on, then we would just say spack, we would do our spack install zlibng again. But this time we're going to enable, so plus IPO. And now a zlibng with that variant enabled is building. That will coexist with our other zlibng. Not every variant, though, is a Boolean. Some take a value, which we can assign with the name equals value syntax. So say we wanted to have debug mode for its build type, we would say spack install zlibng, and again, name equals value, so build type is the name of the variant, and we're going to assign it the value debug. And so now a zlibng with the debug build type is also installed on our system. So some variants are also conditional. So the indented when lines in the spack info output, mark them. So build type, generator, and IPO in this example are only available when the build system equals CMake. So you can only use those variants when CMake is enabled instead of auto tools. And so if you request one of them, that also then therefore would select CMake instead of auto tools as well, since they're conditional on that. Okay, now let's talk more about specifying and constraining ourselves to direct dependencies. If you want to define a direct dependency, that's with the % sign sigil. So the most common direct dependency to think of would be a compiler. You definitely need a compiler. You're directly depending on that. So for this example, let's install zlibng once again, but this time we're going to ask for it to directly depend on Clang. So that's compiled with Clang instead of GCC, the default. So let's say Spack install zlibng percent to specify the direct dependency, Clang. So once again, the fundamental part of Spack is that we can now have all these different zlibungs with their different variants and dependencies, and they're all able to be supported. There are multiple configurations and versions of this are simultaneously supported on our machine. The spec syntax is also recursive, so any syntax you can specify for the root package, which is the package that you're specifically asking to install, we can also use for a dependency. So for example, since a compiler is just another dependency, we can pin its version with the @ sign, just as we did for zlibng. So let's once again install zlibng. But this time, we're going to have a direct dependency. So %sign GCC @ sign version 14. We can also specify transitive dependencies with the caret sigil, so that can constrain any dependency of a root spec, whether direct or transitive. So we need a package with dependencies to try it on. That would be transitive as well. So the tickle package depends on zlibng. So let's preview how Spack would build tickle with constraints on its zlibng dependency using Spack spec. Spec is if you want to see what Spack will decide to build of a package that you're installing without building it first. So we can say spec. The L flag adds the hash of each node. So let's say spec-l tickle with a direct or transitive dependency and direct dependency on zlibng at version 2.0.7 with the direct dependency on that compiler Clang. Also, Todd, were you saying something?
Nope.
Okay. So once that comes back, that's what we're going to call the concretized spec. So Spack has filled in every dependency along with its version, variants, and compiler. So in the output, you can see that the + sign marks those specs that have already been installed. So again, Spack would reuse packages it already has. E marks them as external by the system, and B marks those available in a cache, but not yet installed. So also notice that the % binds to the spec it follows. So because we had a direct dependency on Clang comes after zlibng, only zlibng is the one built with Clang, while tickle keeps whatever the default compiler was. So again, this is also showing how much Spack is doing for you without you having to think about it, about with all these dependencies and what versions you would need for them. Spack is able to create that roadmap and install it for you with all you saying what you do care about. So let's install that version. So Spack install tickle with a indirect dependency on zlibng at version 2.0.7 with a direct dependency on compiler Clang. So by default, Spack installs from a binary cache when it can, rather than building from source. The build-only dependencies a source build needs, such as gmake, are skipped for a pre-built binary. And also each build has a unique hash. So we were showing that again in this -l. You can see, it's kind of hard to see for this part of the terminal, but it's right here what each hash for a spec is. And again, that reflects its complete provenance. So any change to the spec at all, being the version, build options, compiler, dependency, would produce a different hash for that build. So all these different zlibngs that we've installed, they have a unique hash to them with each difference, with all the differences in them. We can refer to a build directly by its hash, but to specify that, you have to put the / so that Spack knows that you're about to put a hash and not a name of a package. So, but for example, rather than rewriting zlib ng at 2.0.7 with Clang again, we can just point tickle at the exact build by its hash. So we could just say Spack. Sorry, here's the zlib ng at 2.0.7 with Clang, and here's its hash. So you could say Spack install tickle with the dependency on / to let Spack know again that we're using a hash, KIE. You don't even have to do the full hash, just enough for it to be unique. And there it goes. It's going to install it, and as you're going to see in the output, it installed it with the zlib ng 2.0.7 and Clang. So similar with Git, generally Spack tries to follow similar to Git, like you have to say Spack at the start of your commands, and we try to follow their logic with things as well. We only need we already talked about that, the unique hashes. If the prefix matches more than one installed package, Spack would report an error and ask us to be more specific. So you're also not going to get in trouble there. We will confirm that it's unique. The Spack spec output above lists the dependencies as a tree, but Spack can also model them as the directed acyclic graph. So a package can be shared by several dependents, which tree can't really show, like you lose some of that information. So the Spack graph command can be helpful of giving you that full graph so you can fully trace where the dependencies lie and if they belong to maybe more than one of your packages. So let's test that out with Spack graph tickle. And once this loads on the output, it has a nice color coding to it, but you can start to see in the documentation that there's a dependency like gmake, and that gmake, well, maybe that's not right. Like this compiler wrapper is dependency on multiple packages. glibc is at the bottom here, and it can just help you understand your build a little bit better. And for more complex packages, Spack graph can also emit dot files to render as an SVG, and if you added the color flag, it draws build only dependencies in a different color. These are similar, or these are the graphs that Todd was showing in the overview before, so it gives you a really nice visual of exactly what your build is. We can also let's move on to a more complicated package now, where we're going to talk about what we call virtual dependencies. So we're going to build HDF5. It depends on MPI, but MPI is a virtual package, which is an interface that several real packages provide. So Spack handles dependencies on such interfaces through virtual dependencies. So by default, if we were to install HDF5, it builds against OpenMPI. So Spack install HDF5. But we might want to build against a different MPI implementation. So if we wanted to see which packages provide the MPI interface, we can ask Spack what that is with the command Spack providers. Also note this nice new terminal user interface, which is new to this release, that we're not seeing as much of a speed up right now because we're already having our binary caches, but when you start to use Spack after this, your builds will go much, much faster, and it looks very clean and pretty. So great tutorial to highlight that. Let's look at the providers of MPI, providers MPI, and you can see that we have all of these different options. So we can request any of these, similar to versions, build types, all of that. So let's install HDF5, but this time with mpitch as the MPI implementation. So Spack install HDF5. with a dependency on mpitch.
and
And we've actually been using virtual packages when we changed compilers earlier, more under the hood. But compilers are providers for virtual packages like C, C++, and Fortran as well. So because these are often provided by the same package, but we might want to use C and C++ from one compiler and Fortran from another, we need syntax to specify which virtual package provides. And for example, we could ask Spack for an HTML5 that uses Clang for the C++ components, but GCC for Fortran. We probably won't run that command right now, but for example, if you wanted to see what that would look like, if we did a spec of HTML5, and like we said, we wanted to use Clang for C and C++ and GCC for Fortran, then Spack would figure out a spec for you that satisfies those constraints. The same syntax works for MPI. We could have written HTML5 depends on MPI equals mpitch instead of HTML5 just depends on mpitch. But there's no need because the only way for HTML5 to depend on mpitch is for mpitch to provide MPI. So let's go over the spec syntax reference one more time, just a review of what we've done so far. The @ sign selects a version or version range. The plus and tilde signs toggle Boolean variants, and the name equals value syntax sets the non-Boolean variants. A percent sign constrains a direct dependency, such as a compiler. The caret constrains any dependency in the graph, whether direct or transitive. The / refers to an already installed build by its hash, and % virtual equals provider, and caret virtual equals provider, pick which package provides a virtual. So you can always come back and refer to these as you're learning the Spack syntax, but once you get it, it's pretty quick to become second nature. Because the syntax is recursive, each of these can be applied to a dependency just as is the root package. But again, there's no need to memorize all of this. Spack help -- spec prints a concise summary you can return to whenever you need it of all of the different things you need to know at Spack. So Spack help, pass the spec flag. There are good examples, definitions, constraints of what versions are like, compilers, all the above. So you can always refer back to that. So now that we have installed a variety of packages, we can use the Spack find command to query which packages are already installed. So we could generally just type Spack find, and it'll give us all of the packages that we've installed with Spack so far. Spack groups based on architecture and compiler used to build each package. And again, like notice some of these might look the same, like a zlibng 2.0.3 or whatever, but that's again where the hashes are useful, and you can add that -l flag to display each package's unique hash to see that there really is a difference between them. As we saw when referring to builds by hash, every installed package has a distinct hash. So configurations that look like in the default output still occupy separate installations, again, like we saw with the hash. Spack find can also show which installed package what each installed package depends on if you pass it the D flag. So for example, let's say Spack find with the dependencies articles. And we can see there's the tickle that we have installed with Spack. And here are all the dependencies that it pulled in with it when we asked to install tickle. The Spack find command can also accept what we call anonymous specs. So those are expressions in Spack syntax that do not contain a package name. So this is again when our MPI example can come in. So if we said Spack find dependencies on mpitch, it'll return every package, installed package that depends on npitch. So there's our HDF5 that we installed with npitch. The find command can also show which packages were installed explicitly and which packages were installed implicitly. So if we do spack find -px, it'll show our our explicitly installed packages, what we also would call our root packages, and the spack find -px shows us the path of where all those installations are. So we can see all the zlib-ngs we installed and the path to them. So let's go into an even more complex example of Trilinos. And now that we know how to use the spec syntax and create installations, let's put it to work on an even more complicated build. So if we first install Trilinos, let's get that going now. It's a complicated package that can have over 30 direct dependencies alone, many of which have dependencies of their own. So only a handful are new here so far. A lot were already installed earlier in the package, so we're going to get to reuse them. But if you were doing this manually, this is where you can start to see that Spack would really save you some time instead of, if you need Trilinos and you want to be using it for science and your purposes of software, you can save hours of time of not only of having to trace which dependencies there are and what's compatible with each other. Spack is able to just do that for you. And you can spend those hours while it's installing doing something else.
And
Once again, Spack manages the consistency of the entire DAG, so every package that depends on MPI is satisfied by the same MPI. So let's install Trilinos again. This time we're using the HDF5 we built with the npitch. So Spack install Trilinos, enabling that HDF5 variant, and having dependency on npitch. So only Trilinos itself was installed and changed. The rest of the graph, including our npitch-based HDF5, was already present and got reused. We can confirm that the whole graph uses npitch with the anonymous spack find caret dependency on npitch. And once that builds, we'll see that that Trilinos exists with that Trilinos is now part of our installed packages that build with npitch. And there it is. Again, this would be a good time to use the dot graphs instead of the ASCII art, because this just has so many dependencies and connections that it would be better to be rendered with a dot graph than our graph command. Okay, now that we've installed our packages, found them, let's go over how we want to, if we wanted to uninstall some of these packages. So earlier we installed several configurations of zlib-ng, so let's go through and uninstall some of those. If we run spack find zlib-ng, we can see all those different zlib-ngs we have, and we uninstall packages by using the same syntax as installing packages. So we can just say spack uninstall zlib-ng with a direct dependency on Clang version 14, or sorry, GCC version 14. And it's going to say, do you really want to proceed? And we can say yes, but it'll catch you there before you uninstall things that you might not want to, or if you already know you do want to install it, you can pass the -y flag in the command line. So now if we do a spack find -lf for the hash zlib-ng, we can see that we went from 7 installed zlibngs to 6, and the specific one that we asked to install is no longer found as being installed by Spack, and it is not installed anymore. We can refer to a package by its hash instead of a full spec, but Spack won't remove a package that another installed package still needs. So if we try to say Spack uninstall zlibng with the KIE again, which is that zlibng at 2.0.7, Spack will catch you and say, hey, before you uninstall that, there are dependents of that installation. So if you uninstall that, these other things will be messed up as well. So we have some guardrails in place. If you did say you wanted to remove it anyway, you can use force. That's up to you. But if you more likely would want to uninstall that, and not only uninstall that package, but the dependents it has, you can pass in the dependents flag or -R for, I believe, recursive to remove it together with everything that also depends on that package. So we're going to say Spack uninstall -Y. Yes, we're sure we want to do it. -- dependents because we want the dependents of this package gone as well. zlibng. And that specific version with the hash, so /KIE. And now not only did that version of zlibng get uninstalled, but also the tickle that was a dependent of it. Spack refuses to uninstall a package when the spec is ambiguous. So if it matches more than one installed package. So if we try to just say Spack uninstall Trillinos, Spack will say, hey, you have multiple Trillinoses. You're going to need to be more specific before I install things. So it's not the alternative of it uninstalling all of your Trillinoses. It needs a specification of which one you want to uninstall. So if we wanted to give a more specific one, let's do it with the hash 66p. And we can say Spack uninstall /66p. Yes. And now that package was uninstalled. Lastly, we're going to go over customizing compilers. So in the installing packages section, we saw that Spack detects the compilers already on your path and configures them as external packages, but Spack can also install a compiler itself and then use it to compile other packages. So for example, let's Spack install GCC @ version 16. And then once that's installed, Spack is able to recognize that as one of its available compilers that it can use. So then once this installs and we run Spack compilers, we can see that GCC at 16.1 that we just requested is there. And we can see that with this plus sign that it was built with Spack. It was not externally found. Also, just to note here that we requested GCC at 16 and then Spack filled that in to be 16.1. It'll default to the and now that compiler is also immediately available to use. So if we decide to do Spack spec czip lib with a direct dependency on GCC at 16, we can see that Spack knows that its game plan would be to fill in GCC 16 for C compiler right here. And it's being used. We don't need this compiler in the next section, so we're gonna uninstall it for now. It is important that you do this step so that when we move on to the next section, it doesn't mess up anything with what your defaults are. So for now, we're going to Spack uninstall -y GCC at 16. So now that we've covered those basic commands, Todd's going to show more in practice what they mean now that you're familiar with it. But once again, we've now seen that we can install from source or binary cache, request specific configurations, query what's installed, uninstall, build and use its own compilers. And this is just the start. So soon we're going to move on to the environments tutorial after that to show how you can group specs, and if you have multiple installations to manage at once, that'll give you a reproducible collection. So thank you, everyone, and back to Todd.
So you saw the basics of how to use Spack from a user perspective from Kathleen. We're going to go through some of the core concepts that underlie what you just saw so that you understand how Spack works internally and what it's really doing when you run those commands. I think everyone should see by now that the biggest difference between Spack and maybe other package managers is that it does support combinatorial versioning. It's not like traditional binary package managers where it's designed to manage a single stack. You can install one version of each package in a single prefix and sort of upgrade it and manage it over time. But you only get that version of the last version, just one version of that package. Port systems are similar, same idea generally with Mac ports, Homebrew, Gentoo, and so on. They really don't have a lot of support for picking specific versions or configurations of packages. And then virtual machines and containers are a way to do this, but you're kind of on your own. You're basically building your own version of a stack in the container, and you're getting everything that comes with the OS with it. So you can sort of think about Spack as a package level containerization tool. It builds isolated package builds so that you can install multiple versions of them. So when you think about Spack, there's really three things that you want to keep in your head. There is the spec syntax, which is really the core of the tool, which is designed to describe package configurations. And so if you think about when you say Spack install MPI leaks, this is unconstrained. It says, get me some build from the space of all MPI leaks builds. I don't care which one. We do try to get you a good one and make reasonable default choices, but this basically just says, get me the preferred MPI leaks version. So MPI leaks really represents all MPI leaks builds. If you say Spack install MPI leaks at 3.3, you're saying I want to add a constraint. So only the MPI leaks builds that are at version 3.3. You can mess with the variants, you can mess with the flags, you can mess with all the other stuff. But get me a decent build of MPI leaks at that version. When you constrain with a compiler or some other build dependency, you're saying get me the builds that have GCC 473 as the compiler, and then Spack picks among those. Same with threads. You're saying enable this variant, inject flags, specify a particular microarchitecture target. We know how to tell the compilers what to do there. And then you can specify the build with a particular version of a dependency as well and constrain that. What we're assuming there is that you're telling us the parts of the configuration that you care about, and not the parts that you don't. And then it's Spack's job to go and choose the rest of the configuration for you. And our job is to make sure that we do a good job of that. And we're trying to make a syntax here where you can basically refer to anything that you could imagine in the build space. And then Spack may not be able to build all the different configuration you can specify on the command line, but at least you can talk about them. The second thing to think of when you think of what Spack looks like is packages. So when you're specifying specs and when you're saying what to install, the names that you use in that syntax are coming from some package repository. So there's a big repository, call it built-in, even though it's not built in anymore, that Spack will download on first use. And that has a recipe like this for every single package you can refer to. And what a package looks like is it's just a Python file. It has a class in it that extends probably some base package for build system support, or maybe not. There's a generic package as well. and it's got a little metadata about that package. So this is script key. You can see here it's got a comment that says it's a simple 3DSN particle transport mini app. There's information about the homepage where you can go to find out more information. There's the URL where you can download it, and then these are the available versions and the checksums that you would use to make sure that you've got that version when you download it. And this is how we make sure that the thing that you get is what the maintainer intended. So when you download a URL here, we check it against the SHA. And Spack is smart enough for most packages to infer the URL from this sort of base URL. So you only have to specify the URL once, and then each version is extrapolated from that. And if some packages will have custom logic for doing that if the project doesn't provide particularly consistent, or if it has weird URLs. These are variants, and they're just build options. So this particular package can have MPI enabled or not enabled. It can have OpenMP enabled or not enabled, and they both default to on here. And then there's dependencies specified down here. So it depends on MPI, when plus MPI, so that's when MPI is enabled. And it depends on CMake at 3.0 or higher, and it's just a build dependency. It's only needed at build time. It's not needed at other times. And you can see that the dependency specs here, these are just specs as well. So we're saying MPI, and that's saying depends on any MPI. You can build it with any one. And CMake needs to be 3.0 or higher. So these are just specs specifying what the valid dependencies are. If you look at this, the metadata up here, the ones that are just function calls, we call these directives, and they specify sort of the space of possibilities of what you can build for a package. So it's very concise. You can specify a lot of different builds with this. So here you've got like 3 versions times 2 values of the MPI variant times 2 values of the OpenMP variant times all the different configurations for different MPI libraries, and times all the different ways that CMake can be built as well, plus all the different possible dependency configurations they can have. So this already defines a bunch of different possible builds. And given this stuff up here, the directives, Spack's job is really to take this space and to pick one configuration within it. And so we have a solver. We'll talk about that in a bit. Call it the concretizer. But it's basically selecting a configuration from the space defined within this package and all of its dependency package recipes. Once it does that, you get this install method down here, and it takes what we call a spec. And in this case, it's a concrete spec. It has all the information filled in. It doesn't have any choices left to make. It's not ambiguous. It refers to one particular build. And these instance methods down here, their job is just to translate the spec, the configuration that Spack picked, into whatever the build system instructions are for the package. And so what you're seeing here is that the 2 variants, the 2 things that are really configurable, Spack's going to download the right source version for you. It's going to untar that. You're going to end up in a directory where you have to run CMake, and Spack's going to translate the OpenMP option and the MPI option from the spec into enable OpenMPI equals true, or enable OpenMPI or OpenMP equals false. And it does that for the MPI variant as well. And these are just package specific. So you're just telling Spack, okay, if I got a configuration that looks like this, then I tell CMake this for this particular package. And often it can be pretty simple. This package also doesn't have an install method or an install target for its CMake system. So we just make a directory in the prefix, which is where we want to install the package. And under the bin directory, we just copy the executable in there for this particular package. And that's it. So you've got space of options, space of all the builds you can do. And then down here, you have the instance methods that say, here's the build instructions. So that's really the 2 parts of a package. And we'll talk more about packages and what you can do in them in the packaging section tomorrow. They can be quite complicated. So we provide a lot of powerful base packages that you can extend. If you look through the Spack ecosystem, there are a lot of packages that depend on CUDA. And most of them extend from CUDA package, which provides you a variant. So if you inherit from CUDA package, then you get this variant on your package. So you can plus CUDA or minus CUDA or tilde CUDA to enable or disable it. And then if CUDA is enabled, you also get a CUDA arch variant so that you can specify the arch level. And so these correspond to like SM levels in CUDA. And then this is very abridged, but just to give you sort of a flavor, we provide a lot of constraints that tell you basically which versions of CUDA support which CUDA arches, so that you know that if you need to build for a particular GPU and optimize for it, that you need a particular version of CUDA. And then we also know how the different CUDA versions are related to different compilers. And most of this is like C++ level and so on, and it can vary by platform how well CUDA supports it. But this is all stuff that you don't have to care about. You can if you just derive from CUDA package when you build your package, you get all of this stuff as a mix-in, and you can go and your user can specify CUDA and CUDA arch correctly. Spack will call them out if they violate any of the constraints, and you can focus on the build logic for your package. So this is just to show that there's a lot of expressivity in the package DSL. Specs can constrain versions of dependencies. You saw this earlier. So if you have a graph that looks like this, you got MPI leaks, depends on call path, and that depends on MPI, Dynance, libdwarf, libelf, and so on. You don't have to know all of the stuff in the middle to say that you want a particular version of libelf. And so that's why you use the caret. It means depends on somewhere in the graph versus the percent, which means direct dependency. So here at Spack install MPI leaks, I want that thing built with Intel. But then somewhere in that graph, there's libelf, and I want it built at 0.8.12, maybe because I know that the latest 0.8.13 version is causing me problems. We do ensure in a graph, or at least in the runtime graph, so the link and run dependencies, that there's one configuration of each library. And so if you're building this application with libelf, and libelf is going to live in the same process as the running application, we are not going to give you a loader race where you have two versions of libelf and you don't know which one's going to get loaded because, say, Dynance depends on one and libdwarf depends on the other. They both have to depend on the same one, and they need to be built with the same one. So that's one of the consistency guarantees that we provide. You can mix and match compilers between different nodes, and you can mix and match build dependencies, pure build dependencies, but you can't mix and match things in the link run graph. Spack also handles ABI compatibility, and it basically source compatible interfaces like MPI. You may have noticed in the package that it depended on MPI, which is not actually an implementation, it's an interface. And MPI has lots of different implementations like OpenMPI, MVAPitch, MPitch, and so on. And you use the same syntax to specify what ought to be swapped in for this MPI node. So MPI is what we call a virtual dependency. It means it's an interface. It can be versioned. And if you want to install the same package but with two different MPI implementations, then you would do Spack install MPI leaks, caret MVAPitch at 1.9, or caret OpenMPI at like 1.4 or higher. And these are just specs like you've seen before. But this is how you specify that this thing should have that dependency. You can also, for MPI in particular, it's versioned. And so the MPI interface itself, MPI 5 is out now, has like things like the binary compatibility standard in it. If you have an application that needs unique MPI 5 calls, then you could write, you could write that your package depends on MPI at 5. And we would pick an implementation that provides that version of the MPI standard. You can also use that on the command line. You can say Spack install MPI leaks with an MPI implementation that is at least at version 2. Generally, you wouldn't write this on the command line. You would put that dependency in the package, but this is just to show that MPI itself is versioned, and we know which versions of the MPI implementations provide which version of MPI. So that's meant to simplify a lot of HPC deployment. If you look at other systems, oftentimes you have to write a different version of your package for each version of MPI that you want to support, whereas we try to allow that sort of thing to be dynamically swappable by the user to simplify the package writing process. And finally, it's Spack. The third thing that you probably want to think about, in addition to specs and packages, is concretization. And concretization, it fills in all the missing configuration details. This is the thing that selects versions, it selects variant values, it makes all the choices for you before the installation happens. So if you say on the command line npi leak, spack install npi leaks, depends on call path at 1.0 plus debug, depends on libelf at 0.8.11. We will take that and turn it into a dependency graph with the constraints that we know about here. This is a simplification of how you can think about it. Spack will then do concretization, which basically fills in all the blanks. And what that means is that for anything unspecified up here, we pick the value of that field in the configuration. So we know that npi leaks needs a version, otherwise we don't know what to download. So we pick 2.3. We know everything needs to be built with a compiler here. And so we pick a compiler version for it. We select some variants and we mix them with the ones that you specified. If there's a conflict, we'll complain. And we pick what we're going to build the graph for. And we then store that in what is now spec.json. So like there's a JSON database of specs. We keep a lot of provenance around so that you can run Spack find and see all the configuration details of the things that you're building or that you've built. You can query that like Kathleen showed. So that's it. In order to manage all this complexity, we have this hashing scheme. And essentially, if you think about this dependency graph, the hash is basically, it's a JSON format, a canonical JSON format of all the configuration information from all the nodes in the graph for a given package. And then we take that canonical JSON and we hash it. And this is just a base 32 encoded SHA-1. It's base 32 so that it's letters and it's a little shorter than like the SHA-1s you might see from Git. And we install that on and that's why you see these hashes at the end of the directories. What that guarantees us is that for any given configuration, we can create a unique directory for it. And we can let all of these different installations that you build coexist together. So that's where we get that from, is from the hash. The other thing that we do with this is because you could have a lot of different configurations installed, we try to ensure that every package knows where its dependencies live. And so if you've ever used LD library path and you've like run a binary and it said, I couldn't find this dependency library, and then you Google it and it says, set LD library path to the path to that thing, and then you've had something else break because you did that. This is the thing that we're trying to avoid with Spack. We use RPaths, which are basically LD library paths that you attach to binaries. They're embedded in the library or the executable. And so every binary in here, like the Python binary, knows where its dependency libraries live. So it has an RPath in it that says, hey, if you're looking for bzip, then go look over in this bzip hc4 sm4 directory. And so you can just run the Python out of the directory without loading modules, without having to know how you built it. You can just run it, and it knows where to find its dependencies. The rationale for that is once you've built a piece of software on an HPC machine, you may come back and use it and forget all the things that you were doing during the build process because it's complicated. We don't think you should have to remember that. We think things should just work the way you built them, and you shouldn't have to remember 16 different modules to load to run a program. And moreover, you might not be the person who built the thing you're trying to run, so you may not have ever known. And so we're trying to keep things simple by embedding RPaths. There is an isolated compilation environment in Spack that allows us to do things like swap compilers. I'm not going to go into the details of how this works, but just know that the build environment gets set up a certain way. We inject our compiler into the build, and so we're really just getting under wherever the build might inject. It might call GCC. We have a wrapper around that puts the RPaths and search paths for dependencies and so on onto the compile line. And what that does is that it makes it very hard to create a build that can't find its dependencies. We're trying to make sure that you build with the right things. And so we make it hard for the compiler to go and find a header, say, in a directory that's not the one where it needs to be for a particular dependency library. Spack supports externals, and you can configure it to use, say, your system MPI. We brought this up in the intro. If you do that, So if you say, you want to build call path library with OpenMPI, you can specify in your packages.yaml that there's an OpenMPI with this spec here that lives in this directory here. So here it's OpenMPI 2.0, blah, blah, blah. And it lives to this path to externals, GCC OpenMPI 2.0.0. And likewise, you can say, hey, there's another OpenMPI over here, and Spack would have a choice between these two to build. If you say buildable false in your configuration, we'll get to that later. It means that don't build one. Always use the ones that I've specified here, and we'll talk about how to constrain the MPI you build with. If you do this, it's sort of on you to guarantee that all of the dependencies of the external that you use are consistent with what the rest of your application uses. And so here, like NPI leaks depends on OpenMPI. It has all of these other dependencies. We're basically chopping off that metadata and we're saying, okay, we trust you. That's your MPI. We're going to build with it. But if it so happens that OpenMPI has library dependencies that are incompatible with other ones, you may run into problems. It is possible now, since 1.1, to specify dependencies for externals. And so you can get a little more metadata under here. You can say, where are the system versions of all the dependencies of OpenMPI, so that you have a bit more provenance. But it's something that you need to set up in package.yaml. And we'll talk a little bit about that in config. Spack has support for external packages. Whenever we do the survey, we usually see that like about 2/3 of our users are writing their own packages and using them from their own repos. And what that looks like is this. You create a repo, you can add the repo to your configuration, and then Spack has it registered. You can list it and see that your repo is above the built-in one. And when you layer things like that, you might have, say, all the open source Spack packages coming from built-in. So that's where probably the majority of your packages come from. So here's like Boost, Raja, and Axum. All those are open source. You may have common internal packages that multiple teams in your organization use, so you can set up a repo for that. And then your team may have its own set of packages that it works on that are private and that you don't want to put out in the rest of the world. You can layer all those things on top of each other in a hierarchy, and this has worked pretty well for teams, at least at Livermore, where we might have the Marble team working with some of their dependencies. They may work on this for a while and then decide that, oh, well, this build of Miranda is actually something that other parts of the organization can use. So they'll move that package, say, into the common repo. And then, ultimately, you want to push something as far down here as it makes sense. So if this is an open source code, it might end up in built-in one day. If it's something that is shared among different parts of an organization or different teams, maybe it just ends up in the local L&L organization and not in the local team organization. You can do lots of different configurations like this for your dev environment and to coordinate among people within an org. Mirrors, which we'll talk about tomorrow, allow you to specify where to fetch things from, and they host both sources and binaries. And so Spack has a built-in source mirror. We try to archive all of the tarballs that people specify in package files in the built-in repo in a source mirror. And oftentimes you'll see Spack hitting that when you download tarballs. You can also put binaries in there, and if you go to cache.spack.io, you can see some of the public binaries. But Spack can fetch from lots of different places. So when you say to install, it may pull from a local cache. Everything it downloads, it sticks in a local cache, and it can fetch from there. You may have a mirror in the shared file system for your organization. You can actually use that to put a mirror behind an air gap if you need to. There may be an S3 bucket. That's sort of where our mirror sits. You can actually use OCI registries as build caches, and so you can pull binaries from there. And then if we can't find things in these places, we'll pull from the original source on the internet. But there's lots of ways to configure where Spack will fetch from. So more on that tomorrow. All right, so it's 10:30. I'm going to leave this last part of the concepts until after the break. So we'll come back in 5 minutes, and I'll finish up, and then we can get on to environments and configuration. All right, so we talked a bit about the different parts of Spack, how there's specs, how there's packages, and how they're sort of tied together by the concretizer, which makes decisions about how dependency should be resolved, how things should be configured. It gets its information from a lot of places. And so we have contributors who are constantly updating Spack packages, adding new versions, new dependencies, new constraints, and things to the packages. And that is one of the places that we get constraints and information about how to build things. Mostly the defaults and what's available for a given package. There are also other places where Spack can pull configuration from. So there's configuration for developers, there's configuration for users. There's configuration that can be in your home directory or in environments. And all of these you'll hear about in the config section. You'll learn a little bit about in the environment section as well. There's configuration that can come off of the command line. So when you say Spack install HDF5 at 1.12.0 plus debug, that's more constraints that go into the solve. And the concretizer's job is to pull all these things together to understand all the relationships of packages with each other and to create a consistent graph. And this problem is NP hard. So it's anything in the graph can, in theory at least, affect anything else. And so we have to have a solver that's capable of understanding how different constraints manifest across the graph and how to find solutions in that space. Turns out there's lots of ways to do that. One of the ones that solvers use is there's Boolean sat solvers. There's custom solvers that use similar algorithms. We settled on answer set programming for Spack because it's a high-level language that looks a lot like Prolog, and it leverages fast sat techniques underneath that give us the speed and correctness that we want. It's also good at multi-objective optimization, which is something that we do to ensure that we pick, say, the most recent possible version or the most preferred version for a package, the defaults for different variants, and so on. So it's a very capable solver, and it improved the maintainability of some of these more complicated configuration options that we have in Spack. And so we rewrote our original Python concretizer in ASP to get completeness. There were places where the old solver would say that there was no solution when there was one. And that got increasingly complicated as the ecosystem grew. So back around, I think like 2018, we introduced this as like an experimental feature, or maybe 2020, 2021. I'm forgetting exactly the time frame. But it's now default in Spack, and our solver is built from code that looks kind of like this. This is the code that's generated for the HDF5 package. There's another file full of rules that tell us how to resolve things, and it's really simplified the maintenance and enabled us to scale the solver. Now, you don't have to know this to use Spack, but this is sort of what's going on under the hood. I'm not going to get into the details of the solver, but I think it's important to understand at least one thing, which is how Spack reuses installed dependencies. And so it used to be that we didn't make any effort to reuse installed dependencies. And we would only reuse things if a hash matched exactly. And so that's now available with -- fresh. You can sort of consider this as like an upgrade command. So if you want your package built with everything the way that it currently is, with the defaults coming straight from the packages, that you can say Spack install -- fresh, say MPI leaks or HDF5. And Spack will reuse installations, but it'll do it in a specific way. It'll go and resolve the graph, so it'll do a solve. It will calculate hashes for every node in the graph, and each of these includes all the dependencies. And then it'll say, hey, is that hash installed? If it is, I'll reuse it. If not, I'm going to go and rebuild the exact build configuration I came up with from myself. And this is how a lot of package managers do reuse. The problem with this is that for a long time we would constantly have users asking, like, why do I have 16 versions of Python? Because they'd keep pulling the package repo, the default configurations would change, and any tiny change in the configuration results in a completely new hash, and you'll get a new build that is just like what's in the package file. That's good if you want an upgrade. That's not great if you just want to get some work done and reuse the packages that you have on hand. So with the solver, with ASP, we're able to tell the solver about all the configuration details for a package. And so here's how we do that. We say, hey, OpenSSL is installed. Here's the hash. Here are all of the constraints that you need to adhere to if you use this particular OpenSSL. And the solver can use these kinds of descriptions to understand which builds it could pick from, and it can also choose to go and build from source. So we have this sort of seamless integration of source and binary packages. Telling the solver to minimize the builds is pretty simple in answer set programming. You just tell it you can choose a hash for any package out of the available hashes. So if there is an installed hash like the one I just showed, you can pick at most one of those for any package. Don't worry about the syntax. You can say, hey, if you choose that hash, you have to impose all the constraints. So you still have to be consistent with all the constraints that might apply to the versions on that package. If you don't assign a hash to something, then you have to build it. And just minimize the number of builds that you do. And this is sort of an oversimplification. If you just minimize builds, there's a little more that you have to do, but this is the gist. And with and without reuse, and reuse is the default now. So if you just install something with Spack, it will try to use all the existing installed dependencies that you have. It can make a big difference. So here's an example where we said, hey, run Spack spec or Spack solve. There's similar commands. Spack solve outputs the optimization criteria on HDS5. And what you can see here is none of these are installed. It's going to build the whole thing from scratch. And because all the cache is missed. And if you run the same solve command but with reuse, then over here you've got CMake, Ncurses, OpenSSL, zlib. There's 16 packages in the graph that can be reused. And if you dig a little bit in these descriptions, what you can see is that this version over here is very, very fresh. It's using CMake 3.21.4. But this one over here is using 3.21.1, which you already had installed. And so that's really the main difference. And then because it was able to just use the older CMake, it's able to use all the things that were built with it as well, in addition to some other stuff. And so you can see here, like CMake 3.21.21 is probably sufficient for what you're doing. And so reuse is a good default. But if you do want the latest and greatest, you can use --fresh to get that. If you want to see what's going to happen with concretization, you can use the Spack spec command. I think there were some demos of this in the basic section. So you can say Spack spec nplex or Spack spec hdf5, and you can supply --reuse or --fresh to this command as well to see what would happen if you concretize with different options. So that's one way to sort of debug your build before you do it. All right, and then just as sort of a preview to environments, there you saw abstract specs, you saw concrete specs, you saw that the concretizer takes what we call an abstract spec, turns it into a concrete spec with all the choices filled in. Environments are basically a way to build customized stacks from an abstract description. It's sort of the multi-spec analog of abstract and concrete specs. You've got a spec.yaml file with some configuration, with a few specs that you want to build down here. So the packages you want to build, we can take the whole environment and concretize it just like we would a single spec, and generate a lock file, which is basically like a concrete spec for the whole environment. And there are lots of things we can do with this. So you're going to see that in the next section, from just basic use cases to tomorrow we're going to talk about developer workflows and how to build stacks on top of environments.
Okay, so like Todd introduced, we're going to be talking about the concept of environments in Spack. So Kathleen and Todd talked about the essentials of how you can use commands like Spack install, Spack uninstall, and Spack find to interact with installing packages, removing them, and querying which packages you have installed within your Spack instance. But at this point, you probably want to add complexity to your workflow. You want to handle collections of packages in a way that is coherent to each use case, and a way that you might do that in different package ecosystems like Python virtual environments or the environment concepts and things like Conda and Nix. We have in Spack, and they're also called environments. So they can do things like managing a software stack with many packages and doing things like specifying which compilers you want each of those packages to be built with, requiring specific dependency implementations for those packages, and essentially doing those to establish a standard set of requirements for a project. You can do things like reproduce your environment on a different machine, on the same machine for a colleague, or environments are essentially self-documenting, so you can document your requirements for an environment as a software stack for collaborators for ephemeral CI/CD pipelines and releases of your software to ensure a consistent environment for development. So Todd briefly mentioned this, but each environment is captured in two files that can be moved around. Spack.yaml is the abstract representation of an environment, and it records the registered specs that you would like to be installed within your environment, things like, HDF5 or Trilinos or some other packages that you may want to explicitly have installed. And that's the abstract representation of what you would like Spack to install. Spack.lock happens after the environment has been concretized, and that includes a complete provenance of each spec that you'd like to be installed, along with all of its dependencies and the resolved build configuration for each of those installations. And we're going to look at those two different files in detail later on in the tutorial. So after the basics tutorial, if we run Spack find to see all of our all of our installed packages, you'll see we have multiple versions of zlibng installed, along with all the other packages and the dependencies that we installed in the basics section. So this shows every single package within your Spack instance. But it's a bit cluttered, and like I mentioned before, if you're trying to isolate different collections of packages based on the use case, like you're developing a single application that needs a list of compilers, a list of MPI implementations, but then you want to move on to another project that doesn't need those things at all. You just need like a Python implementation to be installed in an environment. When you're interacting with Spack, it's helpful to have less clutter and to see only what you're necessarily wanting to work with. And if you install all your packages in a way that we showed in the basics tutorial, you'll end up with something like this, and it'll be difficult to navigate when you need to debug things and ensure the isolation of those installations. So creating an environment is pretty easy. So we can start off by doing spack env create my project. It'll show you that you can run spack env activate my project to activate it. And to see the list of all the environments that we've created so far, you can always run spack env list. And to see whether or not you're in an active environment, you can run spack env status. And because we haven't activated my project yet, we're not in an active environment yet. So let's run spack env activate my project. So we can verify that this worked by running spack env status, and that worked. So at this point, when we run spack find, you'll see that we have none of the packages that we saw before in our previous invocation of spack find. It says we have no root specs, no installed packages, and no concretized packages to be installed, which is expected. So let's just show again what would happen if you ran spack find outside the context of the environment, just to confirm that we didn't wipe anything out with our actions. So we can use the shorthand despacktivate to deactivate the environment, but you can also do spack env deactivate, and that'll do it for you. So let's do spack find, and all the packages that we installed before outside the environment are now available, or are now shown with spack find again. So in the basics section of the tutorial, we installed packages by just doing things like spack install and then specifying the abstract spec that you want to. So you can do that with like specifying the version of the package you want to install, any additional variants that you want to have as part of the build configuration. And you can also do things like configure how dependencies are to be compiled, things like that. So it's not as simple with an environment because we have a concept of what's called a root spec. So root spec is essentially the packages that you want to explicitly have installed in your environment. So to make those available in your environment, you have to add them. So the Spack add command will register a spec as a root spec. So you, for example, if you wanted to have the Tickle scripting language and Trilinos available within your environment as a root spec, you can use the Spack add command to do that. So we'll do Spack add Tickle. And this didn't work because we weren't in an activated environment. So let's do Spack env activate my project. And this should work now. Spack add Tickle and Spack add Trilinos. So now Tickle and Trilinos are both registered as root specs in the environment my project. And they're called roots because they sit at the top of the dependency graph that represents our environment. So let's run Spack find again. And as you can see here, Spack knows that Tickle and Trilinos are two root specs, and you can see that they're not installed by this minus symbol here. We have 0 installed packages and 0 concretized packages to be installed. So we haven't concretized these root specs yet. So at this point, we've added them. We want to concretize them to resolve the dependencies. So we'll do Spack concretize. And so this will resolve the roots, what versions should be installed based on the constraints that we added. So we didn't add any constraints to Tickle and Trilinos, so it should pull the latest versions of those packages. Like Todd mentioned before, if the default is to reuse as many of the existing installations as possible. So if Tickle and Trilinos are already installed, or if any of the dependencies of Tickle and Trilinos are installed, it'll use those as well. So since we already have them installed, you can see that we don't have them installed, but Tickle and Trilinos are both available in the build cache. So you'll see that they can be installed from that cache using the B symbol here. And we can just see what Spack concretized this environment into. So you might have seen in the previous invocations of Spack find that there's a Spack C command, and that essentially shows you explicitly which packages have been concretized but still need to be installed. So we still need to install Tickle and Trilinos after Spack has concretized them. And we can run the Spack install command standalone to take the concretized state of the environment and use Spack to install the packages. So since we're using the build cache, that will be done quite quickly. And we can verify that the installation worked with Spack find. As you can see here, Tickle and Trilinos are both of our root specs, and they've both been successfully installed into the environment. So at this point, we want to use the installed packages. And one of the benefits of an environment is that automatically any of the installed packages, including dependencies and root specs, are any of the files that those packages install as part of the installation process. So things like headers and libraries and binaries. Spack will create a directory tree of symlinks using standard Unix file system paths like bin, lib64, lib, include, and add those to the appropriate environment variables. So when you are in an active environment, or you activate an environment that already has installed packages, those installations will be available within your shell. So we can verify this by seeing if Tickle was successfully installed. We can run which Tickle sh. And as you can see here, the Tickle binary is available in the Spack environment's my project subdirectory under another directory, Spack env view. So when the Tickle binary was installed, Spack when Spack installed Tickle into this environment, it created a view so that you can do things like which tickle sh and run them. And notice that this doesn't only apply to root specs. So Trilinos depends on an MPI implementation. In this case, it installed OpenMPI, I believe, and we can double check that this is available through a review by running which MPICC. And we can verify the version of MPICC by running that. And you can see here that it's using the underlying GCC compiler. We can verify that this works to compile a pretty simple Hello World MPI application using both the MPI implementation available in our environment, as well as another library that is installed not as a root spec, but as a dependency of another package in our environment. So you can open up an editor here. So we're going to create a file, mpi hello.c. And then I'm going to paste in what we have available here in the tutorial site. So it's essentially just importing the MPI header and the zlib header, and then for every MPI rank that it's executed with, it'll print out a hello world. In addition, we were including the zlib from our environment, whatever it can find, based on what's passed to the compiler, and it'll print out the version of zlib and zlibng that was found. So let's compile this with MPICC, mpi hello.c, and then because we're not using a build system, we will have to manually specify the location of the headers. But if you're using something like CMake, if the packages that you're installing have like CMake modules or things that allow other packages to find whether they're installed, that'll be exposed as part of like CMake prefix path or something similar. So we'll do that to compile it, and then we'll double check that it was compiled, and then we can do MPI run with 2 ranks, and then executing a.out. So it did hello world for both of our ranks, and then we can verify that this used the zlib version that is available within our environment view. So it matches 2.33 here and there. And just to show the full set of path variables that were set by the activation of this environment, we can do env grep path. And so as you can see here, we have package config path, man path, AC local path, and the path for binaries exposed by the activation of this environment. And like I mentioned before, if the package exposes things like CMake prefix path and an AC local path, your build system will pick up on those installed packages and use them as part of the build system. So Spack offers 2 ways to, let's say, get rid of a package within an environment. Spack remove is the opposite of Spack add. It essentially unregisters a spec as a root spec from the environment. And Spack uninstall will delete any of the installed files from the disk. So you'll likely end up in a use case where you have multiple environments, and sometimes Spack will, if the constraints are set in a way that Spack wants to reuse many of those installations across environments, you may end up in a situation where you attempt to uninstall something that another environment requires. So let's talk through a use case of how that might work and how these 2 commands interact with each other. So to exemplify this, let's create another environment. So we'll do spack env create my project 2. And then we'll activate it, spack env activate my project 2. And let's add the scalable checkpoint restart library, SCR, and then Trilinos as well. And concretize the environment. And just so you know, in the future, when you're working with environments, the Spack install command essentially does a concretization first if it detects any changes to root specs and does an install. So we're just doing showing how Spack would do it internally, but you can always just do a simple Spack install and it'll handle the concretization for you automatically. So now that this is concretized and we have our root specs SCR and the previously installed Trilinos, let's install it. And now Spack updated the view to any new installations that it did. And we'll run Spack find. And as you can see here, SCR and Trilinos are both installed as root specs. So at this point, my project has Tickle and Trilinos, and my project 2 has SCR and Trilinos. So SCR is only used by my project 2 at this point. So ideally, we would be able to remove it cleanly without any conflicts with other environments. So let's do a Spack remove SCR, and Spack will play its part. It'll remove SCR as a root spec. And just to confirm what happened, after you remove a root spec from an environment, Spack, if you run Spack find, will still think that it is part of the environment because the view that was generated by the concretization will still reflect the fact that SCR is available in the environment, but it will not pick it up as a root spec. But because we made changes to the root spec, you can run Spack concretize, which will reconcretize the environment, and it'll regenerate the view to reflect the fact that SCR was not explicitly requested by any as a root spec or as a dependency at all. And we can confirm this by running Spack find, and as you can see here, SCR and any of its dependencies are not reflected in Spack find anymore. So to go to the use case where you have a package that is installed in 2 environments, Trilinos is available as a root spec in my project and my project 2. So the main way that Spack has decided to deal with this and is useful outside of the context of this use case as well to handle reuse and other features. Environments only point to shared installations of packages rather than owning the file. So the top level Spack instance is the ultimate owner of any installed packages, and environments, when they're concretized and then any packages are built and then installed, simply point to symlinks of what the top level Spack installation per instance has managed. So because they're managed at that higher level, Spack won't let an environment delete the real files from being deleted, and we can confirm this by trying to run Spack uninstall Trilinos from the my project 2 environment. So Spack knows that we're trying to uninstall the root spec from my project 2 environment, but it also knows that the my project environment still references those specs. So Spack remove is the right tool here if you know that you no longer want it in your my project 2 environment. Shouldn't be available in the view at all. You do a Spack remove, and then you'll do a Spack concretize. And we can do a Spack find. Oops, sorry. I meant to activate my project too. Sorry, I meant to activate the original project, my project, to verify that the Trillinos installation was not affected by the removal of the root spec from my project too. And my project obviously still has Trillinos as a root spec. So far we've been treating environments as an abstraction, but they're really just two files and the view symlinks and other metadata stored on disk. So the spack cd command will take us to the my project directory and show us the files that actually represent Spack's understanding of the environment. So we'll do spack cde my project, and then we can check the working directory. So you'll recognize the subdirectory from when we were looking at where the view was generated and where the binaries were available. So it's under the top level Spack instance under Spack environments my project. And to check what files we have available here, it's spack.lock, which is the concrete representation of the environment's packages to be installed or already installed, and spack.yaml, which is essentially a manifest file that stores abstract specs that we specifically asked for, along with any additional configuration settings that define how you want your specs to be concretized or how you want them to be installed, things like that. So spack.yaml is a human readable file. You can do cat spack.yaml, and as you can see here, we have our two root specs, Tickle and Trillinos. We have the views enabled by default. We have the unify feature enabled by default. And the unify feature essentially ensures that all the specs in the environment share a single version of each dependency to maximize the reuse of installations. And spack.lock is not human readable, but we're going to take a quick peek at it just to see what type of information is available within it. So we'll do JQ back.lock, and then we'll look at the first 30 lines. So we have the metadata, so that the version of Spack that is used to generate the lock file, our two root specs along with their full hashes, and then you can see a preview of the type of information that Spack stores about each concretized spec. So the version that we want to install, along with some details about the architecture information that Spack should use as the target for this binary. So spack.lock will record the full concretized environment. So each build can be reproduced exactly when Spack is within the activated environment and has been told to install the packages. So because we are in the Spack environments my project subdirectory, these environments are known as managed environments, and every managed environment can be listed with Spack env list. And the active environment will be highlighted by the output of this command as well. So now let's get into changing our spack.yaml file beyond what we've been doing with the Spack add and the Spack remove commands. So like I said, it also controls the configuration settings about how Spack will behave during concretization or installation. So you might want to do something like require mpitch, like a system mpitch, to be your MPI provider. And you can do this by, so within your activated environment, you can do Spack config edit to open the spack.yaml file. So let's do Spack config edit. And as you can see here, it's the same file that we were looking at before. We have our two root specs, and we can define which MPI provider we want to require for all of our packages with a pretty simple directive. So let's do packages, MPI, require, and then mpitch. will be required to be the provider for any package that depends on MPI. So thinking as if, thinking as we were before, when we make any change to our environment, we'll do a Spack concretize. But Spack, unfortunately, will not automatically pick up on these changes because we haven't made any explicit edits to our root specs. We've only made changes to other parts of our environment, and this change will also affect, which dependencies get installed for the packages. If mpitch depends on something that the previous MPI implementation didn't use before, Spack needs the opportunity to resolve those dependencies together. So we'll do Spack concretize force to allow those constraints to be resolved. So once this runs, all the specs that require MPI will use mpitch as the MPI implementation. We won't install it, but it can be installed if you wish. And one note I want to make here, in general, when you're building an environment, it's totally possible to add a spec, concretize it, install it, add another root spec, make some changes to the package requirements, and go on from there, build the environment incrementally. But Spack will always, in this case, Spack will prefer to concretize each new spec against the versions of dependencies that are already locked in, which can lead to some misconfigurations or some concretizer failures if each package isn't necessarily configured to have similar dependency versions, which can lead to conflicts. So it's usually you usually get a better result if you concretize everything together at the same time, so that any dependencies that are resolved will satisfy all the constraints that your root specs define. So the spack.yaml and spack.log files that we've been using, they're not just a record of the environment that can only exist on your own system that use your Spack instance or any of your installed Spack packages. You can also commit it to like a Git repository, give them to a colleague that's also working on the same system, or drop them into like a CI/CD pipeline that runs Spack installations on a nightly basis. Anyone with the Spack installation can recreate an environment from any of those two files. To demonstrate this, we're going to pretend that we're the recipient of one of these files in a shared environment. So let's create a directory code with make.dir code, change into that directory with cd code, and then we're going to do a Spack env create within this code directory. So rather than creating what we call a managed environment, which you can do Spack env create my project and then have it be listed with Spack env list, you can have Spack generate the environment files within an independent folder. We call that an independent environment. So we can do Spack env create d, and because the environment is independent, as you can see here, the Spack env activate command requires the path to be specified so it can know what to activate. So let's start by editing the spack.yaml file with Spack. We'll, with your editor, spack.yaml, and then we're going to add Trilinos, and OpenMPI as the root specs. We will activate the environment, Spack env activate dot, and then we'll install. Like I mentioned before, Spack install will both concretize the environment and then perform the installation automatically. So the idea is once we performed this concretization, Spack will generate that spack.log file, the concrete representation of the environment. And you'll be able to take either the spack.yaml file that we just created, or the spack.lock file to recreate that environment. So let's first try by using the spack.yaml file to recreate the environment. Let's do this by running spack env create abstract spack.yaml. And then we'll activate this environment. Spack env activate abstract. So when we run spack find, you'll see that we have our 2 root specs that we registered before, but it's not exhibiting any behavior that would suggest that we concretized them, because we essentially took the abstract representation of the environment, plopped it into a new environment, and Spack essentially knows, okay, we have the configuration that the user defined, and we have the root specs that were defined in that file, but we don't know whether or not they've been installed elsewhere in our Spack instance, what we resolve them to depend on. So this allows for flexibility, like if you're passing it to a person on a system that doesn't necessarily have like the same operating system or the same architecture as the one you're building on, and it'll allow them to concretize the environment in a way that respects the constraints that are on their own system. But if you want to recreate an environment with spack.lock, that will that'll use the same exact hashes for the packages and their dependencies to ensure that Spack will only install what is represented in that spack.lock file, which will usually work if you're on the same operating system on the same cluster. But if you are moving between systems or architectures, you may run into issues with actually utilizing the installed files. So to demonstrate how this works, we'll do spack env create concrete spack.lock, and then we'll run spack env activate concrete. Oops, misspelled spack. And then we'll run spack find. So unlike what we saw with the abstract environment that we created from spack.yaml, an environment we created from spack.lock will resolve the same hashes. So because it's already been concretized and because the Spack instance knows that it has installed these specific hashes of OpenMPI, of Churlinos, along with all of their dependencies, when you run Spack find, it'll automatically recognize the fact that they're available for use and will create that view for you as well. So at this point, let's clean up the environments that we created in this section of the tutorial to avoid any conflicts in the subsequent sections. So let's run spack env deactivate. And then let's use the spack env rm command to remove all of our managed environments at the same time. So spack env rm my project, my project 2, abstract, concrete. So now that these are deleted, just want to mention the fact that environments are essentially the building block of a lot of the next parts of our tutorials, so the software stacks, the configuration subsection of the tutorial, along with just being a pretty important concept in Spack. So you can do things like concretizing combinatorial environments for things like HPC, cluster deployments. You can do things like CI/CD workflows, create containers from environments, among other things that I'm sure will be mentioned in the next parts of the tutorial. So yeah, thank you.
Okay, so the next part of the tutorial is going to be the config. We've been doing Spack configuration already in a little bit in basics and in the environments tutorial that Caetano was just giving, but this is really going to be a deep dive on all of the interesting ways that you can configure Spack to allow you to get your deployment of software exactly how you want it. And so as we kind of saw inside of environments, there are a couple of different types of config inside of Spack. These each live kind of as their own configuration files, but the sections from them, either the main config or concretizer packages, we'll dive into all of these more. You can embed each of these sections into environments. So we'll dive into this more, but I just want to say that these parts of config can be reused in multiple places. So if you see something that looks really similar, both inside of an environment and inside of your Spack configuration that might live in your user profile or the defaults that live inside of Spack itself, it is the same and it gets built on top of itself. So the first part, let's go run Spack config blame concretizer to look at what our concretizer configuration looks like right now. So we'll run Spack config blame, insert, and you'll see here that we've got this top level concretizer. You've maybe seen this section before in the environments they were just making because we had Unify inside of there as well. And if you are still in environment, like I forgot to deactivate my environment, you'll see here that that Unify true section is coming from that environment. So this is a good reminder. We should run Spack env deactivate, just to make sure that we're not in any environments anymore. And then you can do Spack env ls or Spack env status, as Kaitana previously showed, to check. It'll highlight one of these as green if you're in one of the environments, and then Spack env status will tell you if you're in an environment or not. So let's go ahead, and we saw before that our concretizer reuse was set to true. So we can see that here inside of our blame for concretizer, that by default, our reuse is set to true. And so you can modify Spack config both inside of the files, like an environment file, but you can also modify it on the command line. So if we want to change our reuse state from true to false, we can run Spack config add, and then concretizer is the top layer of the section of config that we're working in. And then these are kind of nested key value pairs. And so concretizer colon reuse is then the section colon, use, and then false is going to be that value that we're going to set it from here. So we'll go ahead and run that. Now, if we go back and we view the blame from our concretizer, you'll see that we're now set to reuse as false instead of true. And then the next bit is really handily pointed out by the Spack blame command. But the Spack configuration, although it is YAML syntax that you're probably pretty familiar from working on, there's two nuances that we're going to talk about. One is that Spack configuration builds on top of itself. And so we call these configuration scopes. Basically, that you have the Spack defaults, which is what we can see here inside of our Spack installation, what we cloned earlier in basics. There's this Etsy Spack defaults, and then base concretizer is where a lot of these values are coming from. So these environment scopes nest on top of each other or layer on top of each other such that by default, you're using a lot of the default values inside of Spack, and then you can define only the couple of things in your specific concretizer.yaml or inside of an environment that you want to change from the defaults. So we don't have to redefine the entire concretization config every time. We just redefine pieces of it, and then Spack layers on top of these different scopes. New as part of Spack 1.2, I'm going to point out here, is that we have a new functionality that's called Spack isolate. So previously, when you installed Spack, you got the defaults which came from your installation, and you also ended up building up configuration in, say, your home directory and inside of an environment. There are some use cases, like Kaitana talked about, CI/CD systems are a great example of this, but also just if you have multiple versions of Spack installed on a machine and you want to keep all of those versions separate from each other, you can now use the Spack isolate command, which is really a kind of a shorthand wrapper on top of some of the config, to make it so that Spack only looks inside of, essentially just inside of the Spack installation prefix that you cloned. So you can have multiple versions of Spack sitting next to each other, and then they won't be looking at your home directory or any shared location. They'll only be looking inside of themselves. So that's a nice way to isolate Spack from each other. But for this purpose, it's nice oftentimes to have your common configuration inside of something like your .spack directory in your home. Moving on from there, the other addition to regular YAML syntax that we do inside of Spack is that we support a double colon, and we use that for overrides. So in the case that something comes from the built-in defaults, but you don't want either the default functionality or you want to drop, say, you don't want to inherit a bunch of these max dupe configs, you want to drop everything from there, you can use this double colon to overwrite or essentially say, don't nest anything from the lower scopes up into my top level scope, whether that's an environment or your .spack directory. So here, to show that off, I'm going to run spack config blame on the config section. And here you'll see that we have this aliases section. And so we provide a couple of aliases by default for concretize, both with a Z and with an S. If we say wanted to drop all of the aliases that were provided by either our site or that are default inside of Spack, we can add in that configuration with a double colon. So we can do spack config add, and then again, it's the top level section and then any nested keys down to our value. So here we'll do aliases, since that's this section here. And then if you were just to set a new alias here, you just use a single colon. But since we want to wipe out the configuration from the defaults, we're going to do that double colon, which inside of Spack again says drop anything from, like, don't squash the lower scopes into my top level here. I just want to have only what is defined in this top level. So here we'll set it double colon to overwrite equals, and then we're going to do 2 brackets so that it's an empty dictionary. And if we set this, and again, run spack config blame config, we'll see now that we've dropped all of those other aliases from the Spack built-in defaults. So now if you were to go run something like spack concretize with an S, you'd hit an error instead of getting spack concretize with a Z. So here, if we want to view this configuration instead of viewing it here in the spack config blame, we can also see how this double colon and how our configuration renders out, because everything in Spack is basically an editable file at one level or another. So we'll do spack config edit config, and this will bring up in whatever editor of your choice, whether it be Vim or Emacs. We use the editor environment variable set in your shell, so you can set that to whatever you want. For me, it's Emacs because I will totally get lost inside of Vim, but I know a bunch of people use Vim here, and I will make fun of them, or I will try and constrain myself from making fun of them. So here we can see doing spack config edit that we get exactly what we set. The aliases are now set just to that empty list. So here, let's dive now into, I guess, a little bit of a bigger piece of config, which is our packages config. And so if you used Spack before 1.0, and you wanted to either look at or modify your listed compilers, we used to have a compilers section, but in 1.0, when we started treating compilers as regular packages, we moved that compiler section into Spack packages. And so if we want to view our compiler or our other package configuration, we can do spack config edit and then packages for that top level packages section. Also, if you leave off where you want to view the different sections that are available here, doing spack config edit -h, you'll see all the different sections printed here. So let's open up our package configuration. And so you can see here, we have 2 different compilers currently available, Clang or LLVM and GCC, and they're both listed as externals. And so this came up as a question a little bit earlier in basics, but basically like, hey, if I have some software already on my machine, can I not rebuild it with Spack? And yes, we're going to get into that in just a little bit, but the beginnings of it that you can see here are what we call externals, where we can define a spec, and then we can say this piece of software is already installed at this prefix location. And so oftentimes for your software that's coming from your Linux distribution, that'll be in /user, or if you're installing a version of GCC that's not the standard. So here, like GCC 15 is the one that's built in inside of user bin. This one comes from user GCC 14. You'll see like the suffix on those. So here, we can see, like as I was talking about, our two different compilers. You can also see the languages that are supported by the compilers. So if we have a piece of software that depends on C or C++ or Fortran, we can see that both GCC and GCC 14 and GCC 15 support those languages and can compile to them, whereas Clang here only supports C and C++. And so oftentimes we get asked questions of, what if I want to mix my compilers, where I want to say have my Fortran come from gfortran as part of GCC, but I want to use Clang for both C and C++. When we made the transition from compilers as their own separate entity to compilers as packages, this got a little bit more difficult, and so we ended up writing what are called tool chains that let you manage this a bit more easily. So here, let's go spack config edit tool chains. Oh, spack config edit tool chains. Okay, here we'll create a new section called tool chains, and we're going to basically create a tool chain, which is like a named alias of a couple of our settings for the compilers that we would want to use for a spec. So here we'll create a tool chain called Clang gfortran, which, as I was just talking about, uses Clang for our C++ and C implementations, but then uses gfortran or GCC for our Fortran implementation. So here we'll do spec, and here we're going to say basically when something depends on C or has a direct dependency here, again using our sigils. When something has a direct dependency on C, we'll say that that depends on the C implementation that here is LLVM, or Clang, in our case, 21.1.8. And if you were to just add this without the when condition, using this toolchain would force all of your packages to have a dependency on C, C++, and Fortran, even when they didn't, and you would run into, or you'd very likely run into concretizer errors. And so when creating a tool chain, it's very important that we add this when block as well. And so this now says, when I depend on C, use the C implementation that is LLVM. We'll do this again for C++. So when I depend on CXX, I want to use the CXX implementation that again is LLVM at 191.18. When, in this case, we'll say CXX. And then here, because we want our Fortran to still come from GCC, we'll say when we have a direct dependency on Fortran, which is what we call a virtual package, or I guess C, C++, and Fortran are all what we call virtual packages inside of Spack. We'll get more into this tomorrow when we talk about packaging, but we can have multiple implementations of an abstract interface like C, like a language like C, C++, Fortran, where they can come from multiple different compilers. We have this for MPIs as well, where you have OpenMPI, you have MPEG, and VAPEG. They all provide a similar interface for MPI across your center. And so here, I'm just gonna finish writing this out. Okay, So once we've defined our toolchain here, now we can use it as kind of a shorthand alias. Like I was talking about with concretize with an S versus a Z and having aliases, you can think of toolchains as really aliases for the more complex set of mixing and matching of compilers to your own. So here we'll do Spack, we'll look at OpenBOS, and now we can say that we want to have a direct dependency on our toolchain, which is ling g fortran. No, times type that. Spack, OpenBOS. Yeah. I drop here. Oh, yeah. There we go. Apparently, I really want to make it G4 train today. What train? I missed. Or yeah. All right. There we go. So now, if you spell everything correctly, you'll see that we can use our tool chains to simplify when we have a more complex compiler setup on our machines. And we can also use this, or we can also modify our compilers to inject custom C flags or C++ flags. So I'll give an example here. So that if we go into Spack config, edit packages, and then if we want to, under our GCC 14, here we'll have flags, defining this new section, and for C++ flags, we're going to do -G, which enables debug mode. We'll save this. And then as an example, if we want to do Spack spec, zlib, build it on GCC at 14, we'll see here that our C++ flags render out on the Spack spec as a variant. We'll talk more about variants or like defining variants inside of packages tomorrow, but you guys already heard a bit about that inside of the kind of concept section that Todd was talking about earlier. So here you can see we've got our zlib, and then everywhere that we end up using this GCC down the stack, because it tries to do unification to only do a single compiler most of the time when possible, we'll see that the C++ flags are also propagated down the stack when using that compiler. So this makes it a little bit easier instead of having to say, write this out with your C++ flags as -G, and then you would have to redefine this kind of down the stack on different dependencies. Changing it once in your package's configuration propagates to all of your concretizations with that compiler. We can also do this as, I guess, a bit more of an advanced option that I won't totally go into detail, but you can have your different compilers on your system come from modules. So a lot of people on HPC machines, if you're here at Livermore or other sites, will use either environment modules or TCL modules, or LMOD or TCL modules to load software on the different machines. And Spack can say, oh, you want me to use this compiler, or you want me to use this package? If you define the module that it comes from, Spack is smart enough to load that module on your behalf and then go find and use that compiler. Similarly, you might want to inject some extra rpaths into your builds. You can do that via the extra rpaths flag. Or you can also set environment variables. And so if you end up using, say, a compiler like the Intel compilers or other proprietary compilers that require a license file, or you can do this not just for compilers, but really any package. If your package requires a license, you can set that license or like the path to that license file that it expects as the environment variable that it expects when it's used. And then this will be automatically set in the build environments for any dependent packages. So if you're using Spack to build stuff up the stack, you can do that. And then it will be also used when you load the path. So we're running a little shorter on time here, so I'm going to skip that. But if you guys have questions about license files or any of these complex questions, feel free to ask us, and we're happy to answer follow-up questions either today or later tomorrow at the end of the section. So I talked about earlier that we have this concept of virtual packages, and then for packages that are interfaces, something like MPI, something like C or a language. Yeah, so C flags is available, I believe, for all packages, not just compilers, but someone can jump in and let me know if that's wrong. I believe it is now a global for everything that depends on C or C++ or Fortran, that you automatically get those variants. Okay, so back to our discussions of virtual packages. So when you have an interface like MPI or a language like C, and you have multiple packages that provide that interface, we call those packages providers inside of Spack. And so here you can see a long list of, these are all the virtual packages here on the left as the keys, and then the actual real implementations of that interface. So you can see, for example, for MPI, we have two implementations here. We have OpenMPI and we have MPitch. And then the ordering of these is important. Basically saying, by default, if you just tell us that you depend on an MPI and the user doesn't do any configuration, or you don't say that you depend specifically on MPitch, then the first value, in this case OpenMPI, will be given to you first, and then we'll proceed down the list. If, say, OpenMPI didn't fit all of our criteria, we jump to MPitch. But by default, we're always going to give you the thing on the leftmost, which is kind of your higher preference. And we can see that by running Spack HDF5 here. This is just a simple, like very basic, you're not telling, or you're not specifying many hard constraints on HDF5. So Spack is going to do a lot of the work to figure out the best version or the latest version in most cases of HDF5 and all of its dependencies that are going to get to work for you. And you can see here that, oops. There we go, HDF5. I just scrolled up a little too far. Here, when we have our HDF5 instance, that by default, we're going to get it with OpenMPI, like I was just talking about. And if we wanted to, say, use MPitch for a whole bunch of our packages without specifying something like Spack HDF5 that depends either directly or implicitly on something like MPitch, we can do that inside of our config. And to do that, let's create an environment to throw all of this configuration into. As I talked about, your config can either come from files in your home directory, the Spack repo itself, or an environment. This is really just a nicety of, if we do it inside of an environment, we can make a bunch of these changes inside of our environment and then discard in our environment later on for the tutorial tomorrow, and folks won't have that persistent config hanging around. So we'll do Spack env create config env, and then we're going to do Spack env activate config env. And now if we do Spack config edit, you don't have to give any section here, because when you're inside of an environment, all of those sections come from the environment file itself under this top level Spack. So again, concretizer here, it's its own section or can be its own file in many cases, but when you're in an environment, it's all inside of the Spack.yaml file. Asterisk, you can now import and kind of include config from other files. It's a bit more advanced. We're not going to talk about it here. But if you really need to share configuration across multiple environments, you can do that by specifying it in another environment and then using include with the path to that separate file. So here, let's go ahead and we're going to write out a new section, or two new sections, below our concretizer config. One, we're going to write a packages config, and here we're going to say, for everything that depends on C, we're going to prefer, instead of using GCC when possible, to use LLVM. We have two types of keys here, prefer and then require. Prefer tells the concretizer, hey, I'd really like you to try to make this work. Try to depend on Clang in this case when possible. But if you can't, that's fine. You can still fall back and use GCC if needed. Whereas, as I'm going to say here in the MPI section, we require impitch. And so this puts a hard constraint on the concretizer and says, if you cannot concretize with impitch, you're not allowed to fall back to OpenMPI anymore. And it will just error out to you in the case that it can't use impitch somewhere. So we'll save both of these. And now if we run Spack HDF5 again, we'll see that this time we're going to compile with, or we're going to, theoretically we would compile, but we kind of get our dependency graph with impitch instead of with OpenMPI. So here we look inside of here, we'll see that, yep, we're using impitch instead of the OpenMPI that we were going to use before. I'm going to jump back into our environment config here, and I'm also going to say for the top level HDF5 that I'm building, let's just not have it depend on MPI at all. Say that you're building a bunch of serial packages, or you're in an environment where MPI isn't well supported, and you want to make sure that nothing in your stack is using MPI by default. You can, for a top level package, say HDF5, I want to require, and then here we're going to say my spec keyword, basically for all of my specs of HDF5, disable the MPI variant. And now if we come back here and we do Spack HDF5 again, we'll see that this time we get a much smaller dependency tree, and we won't have either OpenMPI or impitch in our dependency tree. So you can see here at this time, it's now disabled MPI, which, as we talked about in the concepts and the basics, tilde disables a variant, plus tools is enabling a variant, and then variants that have multiple values like API here, build system, they're just a key equals value there. So now to follow up properly on the question of external packages. So oftentimes when you're in an HPC environment, you want to install your more interesting scientific software at the top, but you don't care about, say readline or get text, or in this case, we're going to do curl. Oftentimes these things are already in your environment, right? If we run which curl here, we'll see that we get a curl that is just coming from the system, and we can do curl-version to see that it's version 8.18 that is given to us by kind of this base Ubuntu image that we're on for the virtual machines right now. So let's again jump into our environment config, Spack config edit. And here inside of the packages section, you could do this either in the environment like I'm talking about, but for externals in general, you can do this for your whole installation inside of your home directory, inside of that .spack, and then the packages file there. And there, your name of the package, and then we'll define an externals here. So you can have multiple externals, say that there's a base curl that's provided to you by your distribution, but then you also have a curl that's provided by a module. You can have multiple installs of a package here. But we'll say this package, which we knew to be curl 8.18.0, and we know that it was compiled with GCC 15.2.0 here, because GCC 15.2.0 is the GCC version that is just /user/ben GCC, which means it's the default on the system, which really means all of the software around it was compiled typically for Linux distribution with that compiler, and then is such compatible with that GCC runtime and that libc. We know, based off of the which that we ran before, that it is installed into user. And here I'm going to say because this thing is already external, I'm going to mark it as buildable false. This is going to mark curl as an overall package buildable false. And so what I'm saying here is really, Spack, don't try to go off and build your own curl at one point or another. Use the curl that is installed on my system because I know this is going to be available wherever I'm deploying or running, and I don't need to build my own curl. So we'll save this, and again, we'll run spack hdf5. And this time, we'll see that we get a concretization output with these little bracket E's here on the right. We'll see them pop up here on the left as well. But that bracket E means that you're pulling an external from the system. So here, and then again, just the dash means that it's uninstalled, so we haven't installed any of this. The green brackets with a plus here means that this has been installed by Spack. And then if you see the green with a B in it, that means that it's coming from the build cache. That's new of 1.2. We just added that as a new kind of symbol on the side. But it does help users know where their software is coming from more easily. So great, now we can see we're able to use this. We don't need to go build our own curl. We're going to use the curl from the system that's already provided to us. We can do this with more. So we also happen to have an impitch that is provided. We should have an impitch that is provided to us by this version of Ubuntu. And so if we wanted to, we can do spack config edit again. And here we'll define, we said here we want to use MPI, we're going to require impitch. We're going to mark this as buildable false, just like we marked curl as buildable false to say, hey, whenever you need an MPI installation, do not go out and try to build your own MPI installation. Instead, use something that is already built. And so in this case, we'll use the impitch and external that we're pulling in from our system. So again, define impitch externals. We'll define the spec. So I'm going to copy and paste this, but we can get basically our external from here. And then we can again find that this is in the user. If you didn't want to have to write all of this configuration by hand, we can actually close out of this. And we have a nice shorthand inside of Spack as well, which is called Spack external find. Not all packages are externally findable. Basically, they're gated on a small method that is written into each package.py function or package.py file or the packages inside of the repo to say, this is what executables are provided by this package, and if you happen to see them on a system, it means that this package is installed. We also can do some logic for figuring out what version a package is just by matching the kind of -v output, and then we can also figure out what variants in some cases are installed of your package. And so instead of writing out that impitch external, let's actually do spack external find impitch. And so Spack went out and it found that impitch for us. So instead of having to find that ourselves, it's really handy that Spack can, for the most part, in often cases, go and find our externals for us. If you don't specify a package after Spack external find, it will go out and look for everything that Spack can find. This may or may not be what you want. In some cases, it's going to add a lot of system level kind of library low-level packages that are nice that you're not rebuilding all of the time, but it does mean that your software becomes less portable, because if the underlying operating system underneath you changes over time, because Spack wasn't managing those installations, you could end up getting breakages in your top-level package. And so I would say you probably just want to add the externals that you really care about, like stuff like compilers or MPI implementations that are tuned to your specific center. Maybe stuff that takes a really long time to compile from source that we don't have in a binary cache, but I wouldn't use it from everything, just personally. So if we exit out of here and we run spack hdf5, And then we're going to say plus MPI because previously we said that we didn't want our versions of HDF5 to have MPI enabled. So now we're going to reforce it based on the command line. This should go out, and then we'll see that it fails here because we had that requirement inside of the environment. So if we go back into Spack and look at it here, you can see because we have this HDF5 require without MPI, if you give it something that conflicts here with MPI, you'll get a concretizer error. Concretizer error messages have come a long way in the past couple of years, but sometimes they're still not the most intuitive. If you run into a concretizer error that you really don't know how to debug, feel free to reach out on Slack, in the Spack Slack, and a bunch of us are happy to help out with you. Oftentimes, one tip that either Greg Becker or myself give to folks when they're debugging concretizer issues like this is try to make more of your variants explicit, and then Spack will do a better job of handing you an error message that is useful. So, say that I was just installing HDF5 and I got an error here. Oftentimes it helps to say, I want HDF5 at this specific version plus MPI. And then if you make the abstract spec have more detailed information in it, then Spack will more often be able to tell you very specifically, you asked for plus MPI, but we also had our conflicting requirement from your config for tilde MPI. So we can't both enable and disable this. So yeah, try to make your specs explicit when debugging or trying to, you can look through your dependencies through the package.py files that we'll get to tomorrow. And anyway, you can look through that. Try to make them explicit, you'll get better error messages. But if you're still running into something, reach out to us on Slack. A couple more high-level, more advanced features here is to say that inside of your packages configuration, so we have a package that's called Converge. If, say, you're installing a piece of proprietary software, or you're installing a piece of software with a license, or you're working in a code team and they don't want to expose their package to the rest of your users, you only want to let a subset of users read or execute a piece of software, you can do that by underneath the package here defining the permissions. And so this permissions block, you've got read and group here. So you can say read, write, or execute, but read here, basically the read permissions for the package are scoped to the group level, and the group that we want to be able to have read access here are the fluid dynamics group. In the case that you want to go look at the default config for Spack, you can do spack config --scope, and you can give a number of different scopes here. You could look at your environment all the way up to your user, and then all the way up to defaults. If you do defaults config yet edit, that'll print out to you the big default configuration. We have a lot of comments in here that try to make it easy for folks to understand what each of these keys mean. So hopefully that is helpful documentation for folks. You also can configure when you're doing builds inside of here. Oftentimes, or by default, we build into tempfs as scratch space for the build. If you want to move your build stage somewhere that's persistent, say that if you're doing this in a CI/CD system that's fawning out to multiple nodes, and once you get a failed job, the allocation for that job gets cleaned up, you don't have access to the tempfs on that specific node anymore. In that case, you might want to do your build in a kind of network file system, like a globally readable file system between a bunch of the different nodes, so that you could go back and debug that later on. So here you can do the name of Scratch. You can put environment variables in here, so you could do something like $user for your specific user, and then a Spack stage, and that will build into your persistent Scratch space on either a node or across a cluster. We don't recommend this often, but in some cases, some centers may build, the low level, either MPI or compilers may expect an LD library path. We sanitize a bunch of those build environment or build variable or those environment variables from the build by default to try and prevent you from accidentally ingesting an LD library path that isn't inside of Spack already. We try to use our path by default. If you happen to need those external environment variables at some point, you can enable them with this dirty flag where we won't sanitize your build environment before we run the builds. If you're really hitting a bunch of build errors, you can do that. But again, probably reach out on Slack and we can try to help you avoid this. As both Caetano and Kathleen showed earlier in their sections, Spack recently moved to the kind of pretty TUI build installer that builds a bunch of the packages in parallel. And even inside of those parallel package installs, we're using the same job server across multiple packages so that each package can dynamically pull out as many build tasks or as many concurrent GCC compiles as it's able to. If you want to change that parallel configuration, you can do that with the config build job section. So by default, we do J16 in most cases, and then you can limit it, say if you're on a login node or somewhere where you're on a shared machine with many other users inside of, like not in a something like a Slurm allocation, but if you're logged into a machine, typically we recommend log into your machine, go grab an interactive Slurm allocation, do your builds on the compute nodes and not on the login nodes. That's what we recommend to do at Livermore. If you're at a different site that really needs you to be doing your builds on the login node, we suggest it's going to make your builds a little bit slower, but to be nicer to your friends and everybody else that's sitting on that machine alongside you, set your build jobs to 2 or some lower number. So yeah, that is the configuration section. Before everybody runs off, I'm going to say run this Spack config rm concretizer reuse. We set reuse to false earlier in the section so that we could show these differences between MPI and Clang and GCC versions. But if you leave your reuse off in the next couple of sections tomorrow, you're going to notice you're going to basically end up building a bunch of stuff from source instead of reusing the binary cache because we've disabled reuse. So go ahead and remove that with Spack config rm or remove concretizer and then reuse. And then that will delete out that section from our user config. So if we did Spack config blame concretizer, we'll see that we're now pulling that. Oh, I'm still in the environment. Also do Spack UV deactivate at this point. Okay. Now, if we look at that, we still have concretizer reuse as false, but we're outside of our environment. We can remove it here. And now if we look at that, we should see reuse is true, now coming from the Etsy Spack concretizer. I guess for Jeff's question, Spack external find doesn't mark things as buildable false so that Spack can still choose a different version if needed. But by if you determine that you only want to ever use the externals, you can set buildable true or buildable false. It is a little bit like the preference system. If you have an external, the Spack concretizer will try to reuse that external, but it treats it as a preference rather than a requirement until you set something like buildable false, at which point it becomes a requirement in the concretizer.